Number of plastic hinges. The number of plastic hinges required to convert a structure or member into mechanism, means into failure mechanism, is one more than degree of indeterminacy in terms of redundant movements usually. Redundant means unknown. Okay, I have shown that how it works. Here is the formula: n is equal to n plus 1. Okay, n is degree of indeterminacy. If 1 degree of indeterminacy means number of hinges are required 1 plus 1 2 for the forming of failure mechanism in the form of plastic hinges, and for a determinate structure requires only one more plastic hinge to become a mechanism. Means only one hinge is required for the determinate structures. Plastic hinge. It is that cross section of member where bending stress are equal to yield stress. Okay, means here is the stress profile. Okay, here is a stress profile of this beam. Okay, if the stress in the extreme fiber reaches to yield, then at that point plastic hinge formation will start. Okay, it has finite dimensions from bending equation that we already know, that is the basic bending equation. Sigma is equal to stress is equal to my over I. Okay, where m is the moment, y is the distance from neutral axis to the extreme fiber, y, I is the moment of inertia. Okay, that is simple. When it reaches to the yield point, then stress will be yield, moment that will be plastic moment. Okay, and here y is replaced by c, that is just nomenclature, and I is I. Here mp over zp, is I over I, where I over y is z. Z with subscript p is written because plastic. Okay, mp over zp, where I over y, that is section modulus, if the member is in the elastic range, that is the elastic section modulus. When after the yielding, that is called plastic section modulus. Okay, so when the hinge will form, definitely that will go in the plastic range, so that's why zp. Okay, sigma y will be equal to mp over zp. That is the same formula of bending. Okay, just little change. Okay, now the history of loading in the rectangular section. Consider a simple rectangular beam subject to increasing bending moment at the center. Various stress strain stages are encountered as shown. Okay, 4 cases are shown: case A, case B, case C, case D. Case A, when the loading or the moments in the beam less than the yield. Okay, here stress strain profile, when the stress in the beam is less than yield. Okay, so that is a stress profile. And similarly, strain is less than yield, so strain is a linear parameter, so strain profile will remain as it is. Now the second condition, that is the case B, when the moment reaches to my. Okay, when the moment reaches to my, okay, means the extreme fiber, okay, the extreme fiber stress reaches to yield point. Okay, then the third case, first extreme fiber yield, then the lower fiber yielding will start in this section. Okay, here is the section of this beam. First you can see the maximum bending stress at the extreme fiber, so definitely first of all the extreme fiber will fail, then the failure comes under the beam and reaches to the center. Okay, so that's why in the third figure, case C, first of all, due to the increase of the moments before the yielding, means more than the yielding, then first of all the extreme fiber yield, then the first of all extreme fiber will yield, then the next fiber, then the next fiber, Okay, here you can see in the fourth case the yielding continues until it reaches to the neutral axis. Okay, now the whole section is yielded from the top, starting the yielding, it reaches to the neutral axis. The whole section now is yielded. So that is the case for when the strain are greater than yield, much more than yield. Okay, strain profile will keep on increasing, means deformation will keep on increasing. Okay, its shape will remain same, but only the stress profile change due to the yielding of the fibers. Now various stress strain distribution. Okay, case A, stresses and strains are within the elastic range, means less than the yield. Case B, stresses and strains at yield level only at extreme fibers, means case B, the stresses are just reached to the yield point. Case 3, ingress of yield means entering of yielding within the depth of the section, means from the top of the section the yielding starts and continues to the depth of the section. Fourth, full plastification of section. Now the whole section is plastic, means yielding of all fibers occur, okay, in the compression region, in the tension region, in the both region. So that is the full plastification of section. That is the case 4. Okay, here there is two section modulus, that is the elastic section modulus, that is the plastic section modulus. Okay, that I have already shown. That is the same formula. Okay, just multiplied up and down. Okay, if you take the z on the other side, that will be sigma into z, that will equal to m. Okay, so when just the yielding in the case B, when the extreme fiber stress just reaches to yield, so the formula is equal to m is equal to my, okay, equal to sigma y z, means here is the elastic section modulus when just reaches to the extreme fiber up till there, in the first case, in the second case. Okay, in on full plastification, when the plastic hinge will form throughout the section, then sigma is equal to sigma y and m is equal to will be mp, because whole section is plastic. That is for the case 4. Okay, sigma will be sigma y and section modulus will be zp. Now for the calculations for each case. Okay, first of all, for case B, when it reaches to just extreme fiber, okay, here you know the formula. Okay, my is equal to sigma into z. Okay, z is the section modulus, z is the elastic section modulus, that is equal to I over y or I over c, that is the same. Okay, here I, that is a b h cube over 12. Okay, or here that is a d depth. So moment of inertia, that is b d cube over 12 divided by d by 2. Okay, the extreme fiber depth is d by 2 from the center to the upside, that is d by 2. So y is d by 2 I over c, b d cube over 12 divided by d by 2, answer is b d square over 6. Okay, 2 will be cancelled out and it will become 6. So here in the formula just put it there, sigma y into z, instead of z the value is written b d square over 6. Okay, that is for case B. Now let's see for case D, when sigma reaches to sigma y and z reaches to zp. Okay, means elastic section modulus now converted to plastic section modulus. Okay, here m, okay, we can write the moment from this simple formula or from the basic formula. Here in the figure you can see on the upper side there is a compression, in the bottom side that is a tension, and the distance between both, that is a lever arm. Okay, So that's why that is written as C into LA, force into lever arm, where LA is a lever arm. Okay, force into lever arm. Now for the force conversion, B into D by 2. Okay, okay, here is the section. Here, okay, this is the force which will act on this section. Okay, the width of this section is B and the upper portion depth is D by 2. Okay, on which this stress is acting, and the resultant stress, that is a force, that is a compression. Okay, so that's why area is B into D by 2 for the upper portion, that is the area. B D by 2, that is the area, and that is the stress sigma y. Okay, when area into stress, the force will become C. Okay, area into stress, that is equal to force, that is C, and the lever arm, between the distance between these two forces C and T, that is a D by 2. Okay, because the whole section is gone under the plastification. Okay, then the force will act at the center. So total distance is D, and then the half distance will be D by 2. So that's why it is multiplied with D by 2. Okay, sigma y answer will become B D square by 4, and you can see now sigma is the stress and the plastic section modulus is B D square by 4. Okay, you can see in the elastic case the section modulus is B D square by 6, and in the plastics case the plastic section modulus is B D square by 4 when whole section is under the plastification. We can write this formula in the first moment of area form also. MP is equal to sigma y ZP. Okay, ZP can be written as, in the first moment of area, A by 2 for the upper portion. Okay, half area into y1 plus half area into y2, means this upper area into center lever arm from the center of this section, that is y1, and for this bottom, uh, uh, a by 2 for the bottom, that then multiply with y2 for the down lever arm. Okay, you can put the value. Y1 is d by 4 plus y2 again d by 4. So the total resultant from a by 2 into d by 4 plus d by 4, the plastic sectional modulus will be same, that is b d square by 4. Okay, you can also determine by this formula, that is the first moment of area about the equal area axis. Okay, now there is a third case, moment capacity in the elastoplastic range. Okay, what is elastoplastic range? Now you can see in case 3, okay, here is a you can see stress and strain profiles. uh, Means the half of the section is in the elastic range, but the upper portion is gone into the plastic range. So that's why the case C is called elastoplasto section. So that's why the case C is called elastoplasto section. Here the section is shown. Okay, and the region that is plastic, that is depth is Z, just that is a depth, that is not the elastic section modulus, that is the nomenclature of depth. The upper half portion, that is D by 2, lower half portion, that is D by 2. Okay, the lever arm between the elastic sections C2 and between the plastic section C1 and T1, that is the LA1. Okay, so here is the formula, moment formula: force into lever arm, force into LA1, second force C2 into LA2. Okay, for LA1 and LA2, here LA1. Okay, how the lever arm is calculated? we know this z, okay, for this portion. Now for the upper side we want this c1 portion, uh, average of this depth, okay, means from this location we need depth at this point, okay, we need this depth, okay. So how that is calculated? So this is clear z. For the half of this, d by 2 minus z, we will get this depth, and divided by 2 we will get this center, this average, okay. For getting this depth here, la1, okay, z plus d by 2 minus z, this value will come, okay, d by 2, you can see d by 2 minus z, this uh, this length you will get, d by 2 minus z, you will get this length, then divided by 2 you will get this small portion here, d by 2 minus z divided by 2, then this is a whole multiplied, okay. Let me add it, okay, now it's all right, okay. Now z plus d by 2 minus z divided by 2, the whole bracket is multiplied with 2. Why? For the bottom distance, okay, the bottom distance is same. So after multiplying we get d by 2 plus z, okay. Here you can see 2 multiply with z, that is 2z, then 2 is divided by here, that is d by 4 and minus z by 2, okay, d by 4 minus z by 2. When 2 is multiplied, 2z minus that will be remain 1z, okay, d by 2 again cancelled out, will become d by 2 plus z, okay. You can uh, um, check by yourself, that is you will get d by 2 plus z for la1, for lever arm this la1, for lever arm this la2, okay, that is 2 by 3 z multiply with 2. Why? uh, you have performed in the structure analysis many times, to get the centroid of this triangle, from this vertical side the length is 1 by third, and from this side to this side, that is 2 by third, okay. So to get this centroid to this neutral axis depth, so that is 2 by third z. So that's why 2 by third z multiplied with 2 for 2 times for the bottom side also. So lever arm 2 becomes 4 by third z. Okay, we also got for both lever arms, for this lever arm and for this lever arm. Now for the stress of C1, okay, for C1, for the force T1, stress into area, stress is sigma y, okay, in the plastic region, whole section is plastic in the one region, stress into area, area is b into b is the width, and the depth is this of one area, that is d by 2 minus z, okay, that is C1. And C2 for the elastic section force, okay. So here at the center stress is 0, at this point that is sigma y, so stress is sigma y plus 0 divided by 2, we got the average stress, then multiplied with area, area is width into depth, width is width of the section, and depth of the elastic section, elastic portion, that is z. So area is here, stress into area, we got also C2. Now we got C1, C2, LA1, LA2, we will put in this equation, in the moment equation, okay, you can see. First of all, C1, here sigma y b d by 2 minus z, and LA1 d by 2 plus z. Similarly, C2, sigma y zb over 2, okay, and La2 4 by third into z, okay. After simplifying, this is a minus b, a plus b, that will become a square minus b square, okay. Here z will become z square, Okay, 2 will be cancelled out, that will become 2 by third. Now combining, okay, and opening of the brackets, you can see sigma y and b common in both sides, in the whole equation. So now t square by 4 minus z square plus 2 by third z square. Okay, you can perform by using calculator easily. Minus 1 plus 2 by third, you will get the answer of minus 1 by third, z square over third. Okay, that is the value. Okay, mp is equal to mr. Sigma y means when that is reaches to elastic plastic section. Now in the elastic plastic section, sigma y and this portion is called elastoplastic section modulus. Okay, that is the modulus of elastoplastic section modulus of elastoplastic case. Okay, now the next important parameter is shape factor. Why we did this plastic section and elastic section? What is the purpose of that calculation? That is the purpose is shape factor. Okay, it is the ratio of full plastic section modulus moment or plastic section modulus to the elastic moment or elastic section modulus. It depends on the shape of the cross section for a given material. Okay, z shape factor is equal to mp over my. Okay, mp over my is equal to sigma y zp. Okay, sigma y into z. Sigma y will cancel out. Now we can say that shape factor is equal to zp over z, and section modulus is entirely dependent on dimensions. So it varies for each section, for rectangular section, for circular section, for eye section. Okay, let's see shape factor for rectangular section. Okay, for rectangular section, we already know the plastic section modulus and the elastic section modulus. I will not calculate again. Okay, we know the plastic section modulus for rectangular section, that is bd square by 4 divided by bd square by 6. It is just rearranged. Okay, we already know the plastic section modulus for rectangular section, that is bd square by 4. Okay, and the elastic section modulus, that is bd square by 6. Okay, bd square will be cancelled out. The answer is 1.5. Okay, we got the shape factor 1.5. What it means, what is the benefit of shape factor that we got in the rectangular section, that is 1.5. Okay, that is the significance of shape factor. It gives an indication of reserve capacity of a section from a set of yielding at extreme fibers to full plastification. Means how much capacity section have when it reaches to the full plastification. Means it how much load it can take, how much more load it can take before going to full plastification. So okay, we got this idea from shape factor. If my is known, then if we also know the shape factor for a section, we can get easily mp may be calculated because it's a ratio. Shape factor is a ratio. If we know one value, we can get easily the other value. A section with higher shape factor gives a longer warning before collapse. Means it has more capacity, reserve capacity, before the full plastification. A section with higher shape factor is more ductile and gives greater deflection at collapse. Means it gives more warning before failure. Means occupants can go out from the building. Okay, that is the good option. It means higher shape factor is a good. Greater is the gamma value, greater is the collapse load factor. We will also calculate how collapse load factor is calculated, okay, from the shape factor. So that is the benefits of the shape factor. So that's all for the today's lecture for the plastic analysis of steel structure. Have a nice day.